run them up to higher scales. And here they go, all these dashed lines. And you see they don't meet. Of course, 2 of them meet, obviously, but 3 don't meet anywhere, right? There's no one scale at which all 3 are the same. And this means gradient unification just doesn't work as stated in this simple way. Now, the renormalization group is impacted by what particles you have in the theory. So you could just by hand start throwing in more particles to sort of make these things go at different rates and then get them to unify. But the amazing thing is that if you just simply supersymmetrize the theory, throw in all the super partners, which of course have charges under SU2, SU3, and SU10U1, they modify these RGEs also. And you do this exercise again with supersymmetric particles, and you find that if you run them up, their slopes change because of the super partners, and they all meet right here. Okay, so you don't have to do anything to your theory. You basically just take the theory we're talking about, the gauge hierarchy problem, maybe motivated by dark matter, and then you find that when you just run the couplings up, they meet all beautifully at some high scale, 10 to the 16 GeV. And so, this is a hint. Is this significant? Well, it's maybe a coincidence, but again, it seems almost too good to be true. If it weren't, real. And let me just say a couple of things. Some people say, well, come on, 3 lines, sometimes they meet in a point. There's some uncertainties on here, so there's some bands here, so it's not in exactly a point, right? But there's a couple of facts that you should always remember. First of all, they meet. That's quite interesting. But second of all, where do they meet? So they meet at an alpha that is about 21/24 or so here, okay? If they met, say, this is alpha inverse. If they met like down here somewhere, that would be just a purely mathematical fact. It would have no physical meaning because somewhere along here, that alpha has gotten huge. And that means you're in a non-perturbative regime where you can't trust any of this running anyway. So it's significant that they meet here in the perturbative regime. It's also significant that they don't meet at like 10 to the 24 GeV or something above the Planck scale, because again, we wouldn't trust it because we expect new particles to come in, gravity comes in at the Planck scale. So that wouldn't be so interesting. And it turns out they better not meet too low either, because there are particles that come in at the scale and they mediate things like proton decay. And then if we had them at too low a scale, the masses of the particles would be too low and the effects would be too large, and that theory would be ruled out. So effectively what I'm saying is, it's not just that they meet, there's a little box here in this parameter space between 10 to the 16 and 10 to the 18 GeV and perturbative, where they had to meet for any of this to have any possible physical meaning, and they beautifully do. And so it's quite a beautiful story, okay? And if you want to step back a second, it means that if this were true, you would finally understand why SU3 couplings are bigger than SU2 or bigger than U1. It's not just an accident. They start all at the same place, and then they change according to a very well-known renormalization group of evolution, and they come down here, and now that's why strong coupling is strong. Okay. All right, so that's just to say the renormalization group viewpoint is absolutely baked into supersymmetry. Okay, we really think that there's something to starting up here and running things down and figuring out what's down here. So what I'm going to do next is turn to what that means for the masses of the particles. But let me, before I leave this SUSY unification, just ask if there are any questions.
Is this coupling unification unique to only certain forms of SUSY, like this n=1, or is it a common feature?
It's unique to n=1, this exact precise picture here. Yeah, because n=2 would, in addition to all the other problems I noted before, like chiral fermions existing, introduces other particles here, and that would change the running, and presumably without tuning will not lead to such a beautiful relation. So it's an n equals 1 state.
Armin?
So I have a question just about the standard model. Now, the fact that the lines of the three couplings in the standard model don't meet, does this imply that really in the standard model we're missing something at higher energy values that we need to then like incorporate so the beta functions change and of course the volume also so they meet?
Okay, excellent question. So the question is, if you just forget about supersymmetry, just look at the standard model, then they follow these dashed lines and they don't meet. And yes, that means with that sort of minimal standard model particle content, it's inconsistent with the grand unification. So what people have done is say, just put in new particle content at various places to bend these, to change the beta functions, as you say, to bend these trajectories and get them to meet somewhere. So that's another game you can play, but it's a little ad hoc because you can put in different multiplets and you can put them in at whatever mass scale you want. So of course you can do it, but it's not at all clear when you've won because you can do it. You just have to sit there and play with it a little bit. There's no overriding principle there, at least typically. Whereas in supersymmetry, we had this beautiful overriding. Supersymmetry had this overriding principle, and we just did the supersymmetry, and out it comes. Okay, sorry, what is another question?
Oh, yeah. So.
Yeah, I had a question. You said something, you were saying that one of the nice things about the point where these couplings unify is it doesn't happen at too low of an energy, so it doesn't violate experimental bounds. That went by a little fast for me. Could you say a few more words about that?
Yeah, good. Yeah, I went too fast for anybody, really, because there's a lot of detail that I skipped. So we talked about before that if you just put in super partners, you mediate proton decay much too fast. And if you go back, let me go back. There was this diagram which involved, dimension 4 couplings, a scalar to 2 fermions. And that mediates proton decay much too fast. You put in R parity conservation, you get rid of these diagrams, and proton decay is fine again. Except if you also layer on grand unification, that introduces new particles. So what you can think of them as is, you have grand unification, it breaks to smaller gauge groups, SU3 cross SU2 cross SU1. How does that breaking happen? Well, there must be some Higgs-like mechanism, just like the Higgs that breaks SU2 symmetry. So at the gut scale, there's some Higgs-like particles. And it turns out those guys actually mediate proton decay again. And they're not as bad because it turns out they do it through dimension 5 and dimension 6 operators, so more suppressed. But nevertheless, now that the proton decay is known to be, protons have a lifetime of at least 10 to the 34 years, incredibly strong limit. It turns out even those effects could be seen if these grand unified Higgs particles were at like 10 to the 14 GeV instead of 10 to the 16. And so there's a whole story there of figuring out what the proton decay rates are predicted from grand unification and SUSY grand unification, but I haven't really got a chance to describe that in detail.
There was another question, right? Yeah.
Yeah, I have a question regarding the n=1 supersymmetry. There we introduced the gravitino. The gravitino is the superpartner of the gravitone. But isn't it our plan to abandon the gravitone because it's an ill-defined theory, or do we still trust the standard model to be an effective field theory also at the scale of 10 to the 16 GeV, and therefore we introduce the gravitone and we do the SUSY the gravitino?
Mm-hmm. So the gravitino.
In this way, we would get the gravitino not from the gravitone, but from one of the other standard model parts.
Okay, so the gravitino, is in, well, we know that there's gravity in the world. And so there has to be some particle like the graviton. And so although it's not in the standard model, when we think about things like supersymmetry, we supersymmetrize also the graviton. And so there is a gravitino. So in every single theory of supersymmetry, even the MSSM, the minimal one without grain unification, there is a gravitino. The reason I'm not going to talk about right now is that typically it's extremely weakly coupled. And so in terms of phenomena, like I'll talk about these very search experiments and things like that, it kind of sits on the side as a spectator. It doesn't really participate in any of the processes typically, okay? And so for 95% of the SUSY literature, for example, supersymmetry searches at colliders, you will never see the word gravitino mentioned, okay? However, the gravitino exists, and if you think about it a little more carefully, it can have some beautiful roles to play, both in collider physics and in dark matter. And so I will come to that later, but maybe I can reserve more detailed questions about the gravitino until we get there, because I'll set up the formulas a little bit better and provide the context in which these questions kind of fit a little bit better.
Questions? Oh, yeah.
Yeah, if you change the running of the coupling, would that lead to tensions with, for example, electroweak fits?
Okay, so the question is, if you change the running of the coupling, would that lead to tension with weak fits? So not really. So, well, okay, I'm not exactly sure what you mean, but basically, the kind of the game we're playing here is at the weak scale, you have to have the standard model or supersymmetric standard model particle content with all the right couplings. And then that's kind of like, fixed down here. And then if you put new particles in wherever they are up here, they'll adjust things up here, but they won't typically mess things up down here if they're somewhere in the intermediate regime, right? Because they're pretty heavy. Like, a 10 to the 10 GeV particle isn't going to mess up your electroweak fits typically, because it's so heavy. It's kind of most of its effects are decoupled. Of course, if you put them in down here at the weak scale, yeah, they can mess electroweak fits, and they can do all sorts of things, like introduce flavor violation and CP violation and all sorts of stuff that might be constrained by experiment. So you have to be a little careful if you put them there. Okay, thanks.
Okay.
Other questions? I think we exhausted everything.
Okay.
And nothing in the chat, so okay. So I think you're free to keep going, Jonathan.
Okay, very good. Thanks again for all these great questions. So now, in some sense, that was a detour, but it provides the reason I'm going to keep going this way. The second thing, not just gauge couplings run in supersymmetry, mass is spread too. Every parameter in the theory changes with scale. So you can then ask, well, if you start with some reasonable initial conditions at the top scale, and you run down the various parameters, all the masses change, and which mass ends up being at the bottom, which one is the lightest, which is the LSB, okay? And so, well, okay, just a step back, if you don't have any idea what the initial conditions are up here, you can make anything the LSB, because you just tune your initial condition to get what you want down here. But if they're all kind of generated by some uniform mechanism, maybe, for example, well, this is a very strong maybe, the gauginos probably are all unified because the gauge bosons are. So there should be a unified gaugino mass up here, the bino, wino, and gluino, and then they run down just like the gauge couplings do. And you can ask which is the lightest. And the answer is the bino is always the lightest. Okay, the bino is lighter than the wino, is lighter than the gluino, if they all start in the same place. You could do the same thing with all the scalars, the sleptons, the squarks, etc., and run them down. And if they all start in the same place, then you can make a prediction for what ends up lightest when you get down here. And the general fact is that when you have gauge couplings, they push masses up as you go down. When you have Yukawa couplings, they push things down as you go down here. Okay, so there's just that one basic sign fact you should remember. So the gluino has a very strong gauge coupling, and so it gets pushed up very high relative to the wino and the bino. squarks have a strong gauge coupling, and so they get pushed very heavy relative to leptons. And then, within leptons, left-handed leptons have SU2 couplings, right-handed ones don't, so they get pushed heavier. And then even sort of the fine structure of this spectrum, like staus, are going to be lighter than selectrons because they have a larger Yukawa coupling, which pushes them down slightly. Okay. Anyway, bottom line is, if they all kind of start in some unified way up here, similar scales, what typically happens is that among the fermions, the Beano is the lightest, and among the scalars, the stau is the lightest, the right-handed stau. And so those two kind of compete for which one's the LSP. But very, very roughly, in half of the parameter space, the Beano is the lightest supersymmetric particle. And that's beautiful because that is a neutral particle. And that means it's a neutral, stable, cold particle. And it's got the right relic density because of the Wnt miracle. And so it just kind of falls out as sort of this almost ideal dark matter candidate in this sort of context. Okay. All right, now, the keen-eyed among you will notice there's this very weird contour here, which is going down to negative masses. Well, this is really mass squared, so this is negative mass squared. What is going on here? Is this the lightest particle? Well, no, what this is a mass parameter in the Higgs potential. And why does this go so small? It's because a Higgs boson, if you think about it, is the only particle in the theory which has a large Yukawa coupling, but no strong coupling. Right? All the quarks, of course, have strong coupling, and the top has a large Yukawa coupling. But the Higgs, which couples to the top, has a large Yukawa that pushes it down, but no compensating strong coupling that keeps it up. So it actually goes smaller than anything, and it actually turns negative. Is that a bad thing? No, absolutely not, because it turns out that going negative is exactly what breaks SU2. That introduces this instability in the Higgs potential because there's a negative mass square. And basically that pushes your SU2 symmetric theory into a SU2 breaking theory. And so Higgs is the theory. And so this is another fact that seems to be lost in all the hubbub, but supersymmetry has a beautiful understanding of why SU2 is broken and not U1 and not SU3. It's because of this RGE equations and Higgs running negative. Okay. It also beautifully explains why the weak scale is much below the Planck scale, because all this running is logarithmic. And so just with some order 1 parameters, you naturally get sort of an order 1, 16 orders of magnitude split between when this goes negative and where it started. So it provides a context for explaining why SU2 is, the weak scale is 100 GeV and not 10 to the 16 GeV. So it's another beautiful fact of supersymmetry. Another one I like to point out, which is again, something that's not very well appreciated now, but used to be, is that the top Yukawa also runs, and you can start it at a huge range of values up here and run it down, and they pretty much all end up at 1. And so generically, supersymmetry predicts that the top Yukawa is 1, the top mass is 175 GeV, and lo and behold, that's exactly what it is. So there's a lot of sort of circumstantial evidence that this picture might actually be right. But what we're pulling from this is simply, well, the Beano is a pretty darn good dark matter candidate. Okay, so let's go on. So now we have reason to think that the Beano really is a WIMP candidate. And now we can take this seriously and do some hard work. What does this hard work entail? Well, we should calculate its thermal relic density in some well-defined supersymmetry model and figure out, what is it? We know already from the Wnt miracle that it's going to come out somewhere in the ballpark of the right number. But of course, somewhere in the ballpark is not good enough. We've measured it to 1%. So let's do the following. We'll calculate the relic density. The regions of parameter space that give us too much dark matter are excluded. Okay, obviously you can't have too much dark matter that overcloses the universe, makes the universe too short-lived, doesn't work. Regions that give too little are okay, but then BNOs aren't all the dark matter, and you've got to go find some other dark matter candidate, which you can do. It could be BNOs are half the dark matter and axions are the other half or something. But then there's regions that give just the right amount of dark matter, exactly on the nose. And those are then what are called cosmologically preferred regions of parameter space. And sort of by Occam's razor, let's just assume that the dark matter is the BNO. This would be the right scenario to think about. And then we would devote special attention to those regions of parameter space when we're designing searches and proposing new experiments and running colliders and things like this. Okay. So we just then need to determine how the BNO annihilates, what are its annihilation diagrams, calculate the thermally averaged annihilation cross-section, as you've been hearing about, well, even earlier in my lectures, but also in Josh's lectures, and then figure out if it's too high, too low, or just right. So you do that. And what you encounter, first thing is you realize that neutralinos or BNOs can annihilate in an incredibly large number of ways. So this is not meant to be something we're going to go through in detail. It's meant to just impress you that if you really want to do this properly, you have a lot of work to do. There's a lot of different diagrams, and they can all contribute in, some more than others in various parts of parameter space. Thankfully, there are people who have written nice computer codes to do this for you quite generally. But of course, I don't want to think of this as a black box. I want to try to give you some feel for what happens. So out of all these diagrams, you can actually pull out some of the more prominent ones, okay? And they are in two forms. So there's ones where they annihilate to gauge bosons. Here I've shown W particles in the final state, but they could also be Zs. Of course, obviously they can't be photons because photons don't couple to neutral things. And they can't be gluons because they don't couple. This is not colored. So there's just a weak gauge bosons. But okay, so there's ones like this, and then there's ones like this, where they annihilate to fermions, which could be electrons or top quarks or charm quarks or whatever, okay? Given the time, maybe not, let me not go through the details, but suffice it to say that if this is a pure BNO, okay, remember this neutralino is a mixture of a BNO, a WENO, and two Higgsinos. If it's a pure BNO, which sort of happens in much of parameter space for the RG reasons I just mentioned, this is bad because these diagrams don't efficiently annihilate the dark matter. This is easy to see. If this is a BNO, there's no BNO W sort of 3-point vertex for the same reason that there's no photon-photon coupling. Okay, U1 is a non-abelian group. So sure, there are 3 gluon couplings, but there are no 3 photon couplings. And for that same reason, in the supersymmetrized version, there's no 3-point vertices like this, where this is a U1 gaugino. So anyway, you can go through and work out the details, and this has been done. I have some notes here, and it's also described in the written notes I sent. Basically, the way to organize your thinking in this parameter space is, if this is a pure BNO, these don't annihilate very well, and you get too much dark matter, that's excluded. So what you need to do is look around for mechanisms which help the dark matter to annihilate, to enhance the annihilation, to bring down the omega dark matter. And so this has been done. And there are a number of ways to enhance the annihilation and to get yourself into a cosmologically preferred region. And so I'll just show 3 examples because I think it ties in nicely with some of the other things we'll be talking about and also in other lectures. So, okay, so let's start here. So this is some parameter space, okay? And of course, supersymmetry has lots of parameter space and lots of different models. This is probably the most famous simplified model where you have a general scalar mass, a general gaugino mass, and a couple other parameters are suppressed on this plot. And you can figure out where in this parameter space you get the right amount of dark matter. And it turns out in this white region in here, the BNO is the dark matter and omega BNO is too big, as I mentioned. So kind of a large chunk of this parameter space is ruled out because you have too much dark matter. But then in the yellow and better, the green regions, you get just the right of dark matter. Okay, these little ribbons that run through here. The fact that these are very thin ribbons is not really something you should hold against supersymmetry. It's just simply the fact that we've measured the dark matter relic density very precisely. And so the more precisely you measure it, the thinner this gets. But the question is, what is going on in these different green regions here? And so there's kind of three regions. There's something called the bulk region, co-annihilation region, and the focus point region. So what's going on? Okay, well, remember the strategy is to enhance the annihilation. So let's talk about the bulk region. Here you have this one diagram, and it's generally not a big enough cross section. You can make it bigger by making, say, this fermion in the T channel lighter and lighter and lighter. Of course, you can't make it too light, because if it's lighter than the neutralino, then the neutralino is not the dark matter anymore. So you also have to make the neutralino lighter and lighter and lighter. And you have to bring them down to about 100 GeV. Okay, so this theory would predict sort of 100 GeV dark matter and 100 GeV leptons. Okay, that would work in terms of the relic density. This region over here is called the co-annihilation region. Here, what you do is you bring along another particle to help the dark matter annihilate. So I know you just heard about this in the dark matter production lectures. Co-annihilation is another way where you have some other particle, like this case, the stau, which annihilates with the neutralino, far stronger than the neutralino annihilates with itself. And so you can bring the neutralino annihilation rate up, the relic density down, by having this happen. To do this, of course, you have to have staus in your theory when the neutralino is freezing out. So typically they have to be fairly degenerate, okay? But okay, you can arrange that, and that's exactly what happens in this little region here. And so you have, maybe just to give numbers, like a 400 GeV dark matter candidate, a 420 GeV stau, and everything works out really nicely. Okay, let me finish off with this first. Then there's the third region, this is called the focus point region. And this one, what you do is you say, well, this whole problem stemmed from the fact that the BINO didn't have any of these three clean interactions. Let's make it not just a BINO, but have some hexeno component to it. And that's what happens in here. And then this turns out to give you the right relic density too. Okay, by just basically mixing in a little bit of hexeno with the BINO. Okay, so those are three different strategies that have worked. And of course, what you want to do next is say, well, what do these imply for all sorts of searches? Okay. So let me, before I go on, there's a chat question: in the non-relativistic regime, doesn't non-perturbative effects enhance the cross-section for the neutralino annihilations? So everything is perturbative, but I think the question might be referring to things like Sommerfeld enhancements and stuff. And so, yes, if you look more in detail at calculating things like this, there are sometimes other diagrams that are not these sort of leading order tree diagrams. And in particular, there's a whole class which involves sort of stringing across various particles across these propagators here. And those can enhance the annihilation. And so probably the best known of these is called Sommerfeld enhancement. And that was actually something that was discussed quite a lot. And so, yeah, that could modify things. And yeah, in the chat, the question clarifies that it is in fact Sommerfeld enhancement that we're talking about. Okay, so let's see, should I go on? Oh, sorry, there's a question, go ahead.
Thanks. So I think I understand like the processes that are causing these three regions to exist, but I don't quite understand why the green ribbon has that kind of U shape in this parameter space.
Okay, well, to understand that would require actually, understanding more about the minimal supergravity model that is in the context of, and also renormalization groups. And so that's what leads to these phrase behaviors. But generally speaking, it's not so easy to understand. But I can give you an example here. So this is the scalar, this is kind of governing scalar masses, this axis. This is governing gaugino masses. And so if you're up in this region, the scalars are very heavy. If you're way over here, the gauginos are, sorry, if you're, let's see, how do we do this? There's a line on which, scalars and gauginos are roughly degenerate. And then on one side, you'll have that the scalars are heavier. On the other side, you'll have that the gauginos are heavier. And so, for example, over here, the gauginos are the lightest. In this red region, the stau is the lightest. And so that's excluded because you have this charged dark matter. And right on the border, you have the region where the gaugino, chi, and the stau are sort of degenerate. And so that's why the co-annihilation region just sort of, hugs this border here. But in general, the whole U-shaped thing is very complicated and it would take a lot longer to understand that in detail. Okay,
Okay, thank you. I'll pick up a Susie textbook.
Other questions?
Yeah.
Okay, I think we can continue.
Yeah, okay. Okay, so then, what you do is, given these cosmologically preferred regions, you could ask, well, what are the implications for all sorts of things? So, first thing is that the light SUSY, this bulk region where we predicted 100 GeV leptons, that those are just not viable anymore. They were not viable already at LEP, but LHC has excluded 100 GeV leptons. So this might have been a good idea, but is experimentally excluded. And you can go through these other regions. Full focus rate region, it turns out, is most stringently probed by direct detection, which I will mention. Co-annihilating dark matter is still viable. And in fact, if you want to find a solution to the G-2 of the muon problem, you can look in this region and find one. Susie can explain the G-2 discrepancy. Outside of the CMSSM, you can look for other things like we know like dark matter, which has to have a mass of like 3 TeV, and that's most stringently probed by indirect detection. It's hard to see 3 TeV. We know that the LHC are direct detection, but works great at indirect detection. Anyway, so basically the bottom line is this then sort of leads you to a whole bunch of phenomenological studies of details of how to find dark matter. The thing I want to just point out here is that if you'll notice, a lot of these things actually consist of upper bounds. So this region only exists up to masses of 600 GeV. This one only exists up to masses of a TeV. This one, the mass range has to be 3 TeV. This is a super interesting thing because, the great complaint about supersymmetry is that you can never exclude it. You could just, you run an experiment, you don't see SUSY, well, then the theorists go back to the drawing board, push all the mass scales up. And, you then have a viable theory again, it's just that everything's heavier. And that's irritating. The interesting thing about cosmology is you can't, in some sense, in a very general sense, you can't just keep pushing masses heavier and heavier. Because when you do that, you make all the cross sections smaller, you decouple things. And when you make the cross sections smaller, you make the annihilation cross sections smaller, and then you have too much dark matter. So it's a beautiful synergy between particle physics and cosmology, that particle physics is always coming at things from the low end, excluding light things. Cosmology in this context is coming from the high mass end and excluding high masses. And so at least in this context, you have the hope that you can actually completely probe a region by considering both cosmology and particle physics at the same time. All right, finally, we get to the next section. Again, I'm running late, so let me barrel on ahead and talk about WIMP detection. And I may skip a few details here as I go along. The WIMP detection, basically, the idea, and this is sort of laid out in this figure I made a while ago, which sort of gives you a picture of what the basic strategy is here. So in WIMP detection, there are 3 ways to do it. You can look for indirect detection, where dark matter annihilates to some standard model particles. You can look at direct detection, where dark matter scatters off of some quark in a nucleon in a nucleus somewhere and leaves some energy here. That's direct detection. And then you can make it by smashing together quarks and a proton, say, and making dark matter and look for dark matter there, okay? And so this is sort of this three main ways to look for dark matter. This is called indirect detection. This direction is called direct detection. And this direction is called particle production at colliders. The interesting thing about the WIMP miracle context is that this is also the diagram that governs how much dark matter there is, right? This annihilation, chi to QQ, going down the page, is what's setting the relic density. And you know that can't be too weak, as I just said, because then you have too much dark matter. And so that's excluded. And so just on this very general grounds, summarizing everything in this 4-point blob here, obviously I'm very, very general. The point is that if you want to have not too much dark matter, again, you can't decouple this blob. You can't make this arbitrarily small, which means that not only does it tell you that the annihilation has to be at a certain rate, which is good for indirect detection, but it kind of tells you that direct detection has to be at a certain rate, which provides a lower bound for direct detection, and the production at colliders has to be at a lower rate, so that there has to be some, rate at colliders. And so this is, again, this beautiful fact, okay, that cosmology provides upper bounds on masses, and in some sense provides minimal rates, sort of target rates for all these processes. And so it's just not a hopeless bottomless pit task, that now you have some targets to shoot for. So, okay, so I would like to talk about these three, but this will take some time. So let me see how far I get here. So direct detection, of course, you have some beautiful lectures coming up about this next week. So I won't go into the details, but basically, let's just review some basic facts, okay? Maybe we can use this as setting the stage for Joe's talk. So the WIMP, what are its basic properties? It has 100 GeV mass. It has a velocity of 10 to the minus 3 now. Okay, recall that it's much less relativistic now than at freeze out. The local density is about 0.3 GeV per cubic centimeter, or about 1 per liter. And that's, of course, determined by the mass and the total sort of mass density. So this is the this is the mass density. The number density is, of course, determined by the mass. And then the kinetic energy is going to be just mv squared. So this is 100 GeV. Now we're down to 100 keV. So that's setting the scale for what you need to do. You need to have some experiment that's able to see that particle physics standards extremely small energy deposits at the 100 keV level, and to do it with as much precision as possible, a few events a year, for example. Now, for dark matter in the 100 GeV range, we would most like to scatter it off of something that's similarly matched in mass. So 100 GeV nucleus is the best thing to do. And this is because we're trying to get significant energy transfer to the nucleus so that we can have something visible like a nucleus recoil and see that. And if you match the mass of the colliding objects, you get the most momentum transfer. And so you want to scatter off the nuclei in standard matter, not electrons, okay? And then you look for various nuclear recoil signals, like phonons, waves in some condensed matter system, scintillation, light ionization, something that tells you that something came into your detector, bumped off of it, and left the signal. I'll skip these, but well, this is just yet some of the really fun stuff. Before you dive into the details of how lux or xenon work, you might want to have the big picture in mind. And one question is, what are the upper bounds on the dark matter cross-section, scattering cross-section, and what are the lower bounds? The upper bounds, you might say, well, let me just go to lux or xenon or whatever the latest Panda X detector is and see what their upper bounds are. But that's not actually a complete answer, because you could have dark matter that scatters so strongly that it just never gets to your detector underground, right? You can evade all these beautiful experiments deep
Jonathan, you
underground.
have a raised hand in the chat.
Ah, okay. Let's see. So I
Hey,
don't
may
see anything in the chat, so maybe just speak. Yeah.
Yeah, may I ask you? So I have a question regarding this, for example, indirect detection, because you said that we have to have cross-section to be sufficiently large, otherwise there would be too much of dark matter. I wanted to ask, how do we know how much of dark matter initially there was, so we can say we have to decay it efficiently?
Oh, well, so this was in the sort of WIMP thermal freeze-out context, where you assume that dark matter was in thermal equilibrium in the initial hot universe. And so you had a thermal relic, or a thermal equilibrium number density. And so that sets the initial condition, just basically whatever the requirement is of being in thermal equilibrium. Is that clear?
Yeah, thank you.
Okay, and then there's a
There's
question in
another
the
question
chat.
in the chat if you see it.
Yeah. Yeah, you mentioned a few times that the WIMP velocity is 1/3 at freeze out, in contrast to much lower values today. How can the decoupled dark matter particles slow down after freeze out? Well, they basically, I guess there's two effects. One is that the universe expands and also particles bump into each other. And so, yeah, basically, you know, in great detail, how the initial very uniform velocity distribution ends up looking like what we see now, dark matter organized into halos and things like that. That's a detailed question. And I guess perhaps Anne mentioned that. That has to do with the dark matter distribution and the velocity distribution and galaxies and things like that. But the general slowing down is not a problem. Okay, so let me go, I don't see any more questions. Let me go back to this. So I was just going to point out that dark matter that's extremely strongly interacting will avoid all these underground detectors because it'll say stop in the atmosphere, or certainly in, you know, the first 1 meter of the ground if they encounter the Earth. And so actually there's a very interesting story here of how strongly interacting dark matter is ruled out. And at least a little more than a decade ago, there were actually patches of the parameter space. This is the dark matter mass and the dark matter cross-section, scattering cross-section, which were not ruled out. But now it seems that they're ruled out. But again, this is an area that there could be more work. There's an incredible variety of constraints on this. Some of these are crazy experiments where they launch a rocket up into space. It goes up, takes data for 30 seconds, falls back down, and you look and see if there was evidence that dark matter hit your detector in the rocket. So anyway, it's a very interesting story here. Bottom line, though, is that it seems that very strongly interacting dark matter is ruled out. And so what we need to do is push down to lower and lower cross sections. You might ask, well, okay, what about the lower bound? What, you know, when can we stop? And the answer is that you can never really stop, but there is a point at which things get very difficult because at some point the neutrino background comes in. So we know that there are neutrinos which have a variety of sources, solar, atmospheric, and even diffuse supernovae background neutrinos. And at some point, that neutrino rate will create signals in your detector, which look for all intents and purposes like dark matter. And so there is a limit to sort of the background free, non-directional direct detection searches. And that will be reached by 10-ton experiments, which are probing cross-sections of the order of a yoctobarn, which is 10 to the minus 3 zeptobarns, which is 10 to the minus 12 picobarns, which is 10 to the minus 48 centimeters squared. Okay, so this is commonly called the neutrino floor. Dark matter is not necessarily going all in the same direction as neutrinos. Obviously, for example, solar neutrinos have a directionality, And so if you're clever and you have a dark matter detector that can tell which direction the signal is coming from, you could go beyond this neutrino floor. Or if you simply just have an enormous detector and see rates that are beyond the neutrino rate, but background-free non-directional direct detection has this problem, which is coming up. Okay, so one then has this task ahead of you, which is that we have some, say, supersymmetric theory. We have some dark matter candidates. We can, at least theorists can, calculate the scattering and interactions with quarks, okay? But the quarks, no one has a detector composed of quarks. We have detectors composed of nuclei. So what you have to do is get from this fundamental level interaction, dark matter with quarks here, and convert that into first interactions with nucleons, protons and neutrons, and then interactions with nuclei, which are actually the things that are observed in experiments. And so there's a very long process to do this, but let me just try to outline in broad brush some of the main features. The first is that there are, say, if you had terms like this and terms like this, if you take the non-relativistic limit, which is fine because we have dark matter at velocity 10 to the minus 3, then what this turns out to be is a spin-spin interaction between dark matter spin and quark spin. Okay. And so this reduces to spin-spin interactions, which rely critically on the dark matter having a spin, that is a fermion, say, not a scalar. And then these things are spin independent. And in some sense, these interact sort of with mass, okay? And so there's a dichotomy right off the top between spin independent searches and spin dependent searches. I'll just talk about spin independent in this lecture, but spin dependent is also very interesting. The critical thing is one can then build up from the quark interactions to nucleon interactions. And let me just say that in the end, the interaction with a nucleus typically is written in this form. And so you have some interaction strength with protons times the number of protons, plus some interaction strength with neutrons times the number of neutrons. And then that's squared. The amplitude is proportional to this, the cross-section is proportional to this squared. And that gives you the interaction cross-section with some nucleus, with some total number of nucleons A, okay? So this is what sort of is generically true. And then you see you have an FP here and an FN. Generically, these are not necessarily equal, but what people do is they basically typically report results assuming they are equal, so that the dark matter interacts with a proton and the neutron exactly in the same way. If we go to this formula here, if FP equals Fn, then of course this whole thing is proportional to A squared. And so, give me a nucleus, xenon, A is 136, okay, then there's 136 squared. It's important to note, however, that the dark matter sees the whole nucleus and not the individual nucleons because it's so low in energy. And so that's why you sort of sum the proton interaction and the neutron interaction first before squaring, okay? But what this means is that if this FP is equal to Fn and this cross-section is proportional to A squared, then bigger nuclei are better because you get this coherence, right? So if you have a 1-ton detector, it's much better that it's in the form of lead than in the form of hydrogen, okay? Or maybe more relevantly, it's better that it's in the form of xenon than it's in the form of germanium, okay? Because if you can group these things into big nuclei, you're gonna be enhancing things. But this relies crucially on this fact, okay? So when you step back and see limits, always remember that there are assumptions, sometimes strong assumptions that go into these plots. Okay, so let me go on here. So there are a bunch of great experiments that you'll hear a lot about that are looking for dark matter here. Here's the latest plot. So here's the WIMP mass from 10 GeV to a TeV. And here's the interaction cross-section. Here's a zeptobarn right here. And these experiments, plot limits. They haven't seen anything yet. And there's strongness around 100 GeV for the reasons I mentioned, when the mass is similar to the nucleus mass. And these are getting to be they're like 1 ton scale experiments right now. Here's a photo of what is this, Xenon, Lux, and Panda X. But let's just sort of evaluate where we are in the grand scale. So here is the mass plane again, and the interaction cross-section plane. There's a bunch of limits which were set in 2012 and earlier. There's also some regions of parameter space which are not bounds, which are claimed signals, most famously from Dama here. Okay. And then since then, there's been immense progress. So at that time, okay, first there's the neutrino background here, which I mentioned. This is the so-called neutrino floor, which is down here. And you see we've still got, at that time, 5 orders of magnitude to go. The WIMP miracle basically is telling us we should have dark matter somewhere in this 10 GeV to several TeV range. Okay, so that kind of favors this shaded region. If you had Higgs mediated scattering, it favors a particular cross-section range in here. And so this is sort of a very interesting target range. And then you can ask what's happened since 2012. And the answer is that incredible progress has been made. So sort of the latest would be things like Lux, Xenon 1 ton, which have gone down, as I say, down to sort of levels like this. So we're kind of halfway down to the neutrino background compared to 2012. And then there are even larger experiments, multi-ton experiments that are being planned to sort of push down even further. Okay, so that's sort of the status of direct detection. And various WIMP models, SUSY models predict signals in this parameter space. Okay, so I see another question. Okay, so I think that's a question maybe we'll leave for the question
Sorry,
and answer
Jonathan,
time.
I think you just got muted.
Okay.
My question was, maybe I just missed this, but why do we like the idea that the Higgs might be mediating that interaction? Like, why was that part of the parameter space highlighted?
Okay, yeah, good question. So, you can think of what is mediating the dark matter interaction, and it should be like, say, for example, a Z boson could do it. This is a weakly interacting particle and it has weak interactions. So the Z is a weak gauge boson. That would work. And it turns out if you do that, then your interaction cross sections are up here. And so in fact, this was a target decades ago. And we've now run through that whole idea, and that's killed off a whole bunch of dark matter candidates, for example, including this neutrino, which interacts through a Z. And so you could think about Z mediated, but they're gone. And so what's the next? Well, the next good candidate is Higgs mediated ones, because those are, very generic. And so they give a target down here. And so it's not necessarily, in some WIMP models, those are the dominant ones, and some they aren't, but it just gives you a feel for kind of the region of parameter space that we're probing at the present time with the state-of-the-art detectors.
Thank you.
Any other questions?
Anything else? Okay, I think we're good.
Okay, let me go on. There's a question in the chat about dark matter velocities. Sorry, let me just keep going on because I don't want to get too far behind. Okay, so next is indirect detection. And so here you have dark matter annihilating with itself, nowadays. And this continues to happen. It happened in the early universe. That's what set the thermorelic density. It happens now at a rate that's far too small to really change thermorelic density. but sufficient enough that if you have some nice experiments, you can see evidence of this process. And so what are the possible final states? Well, basically everything you can think of. So you could make photons, neutrinos, positrons, antiprotons, antideuterons. Of course, you can make deuterons, you can make protons, you can make electrons, but there's a lot of those already in the universe. So we typically look at the antimatter. The essential thing to point out here is that because this exact same process gives you the relic density, you have much better control on how this is happening now, assuming that the process is S-wave, that it's not velocity dependent, than you do in scattering. Okay, in scattering, you have to tilt things and do crossing or something. Here, you're just doing the exact same process as in the early universe. And so we have a target annihilation cross-section, which is this. And this is, a specific realization of what I mentioned earlier. Cosmology provides some sort of targets that are very interesting for experiments. So this then turns into a game of what, at least when I was a kid, we called Mad Libs, where you fill in these blanks. So dark matter annihilates in a place to some particles, which are detected by some experiment. And what you do is fill these 3 blanks in with the right words, and you get $10 million and you go and look for dark matter, okay? So, obviously not all the ways to fill this in are as good as all the others, so there's some preferred ones. Let me just mention a few. Photons are a great way. Of course, photons are what astronomy is all about. So dark matter could annihilate in the galactic center or in dwarf galaxies to photons, which could be detected by Fermi or CTA, the Cherenkov telescope array, etc. Okay, and one then calculates a flux. There's of course some dependence on particle physics because you need to know what the cross section is and what are you annihilating to. And then there's dependence on the astrophysics, namely how is the dark matter arranged, say in our galaxy. So what is, you look in a certain direction, what is the line of sight integral of rho squared, which is basically telling you the number density squared, and tells you, how often you have annihilations. And so there are 2 kinds of signals. You can look for lines from dark matter annihilating to 2 photons, or to a photon in Z. This, of course, doesn't happen at tree level because photons don't couple to neutral things. So this is loop suppressed. But because dark matter is at rest, basically, this gives you a line. So, this photon from a photon-photon final state is going to have an energy that's exactly equal to the dark matter mass. And so you should, be looking around, and all of a sudden at the dark matter mass, boom, you get this huge giant signal, and then it stops. And so that's a very distinctive signal. And incidentally, if you saw it, you would then have a measurement of the dark matter mass. Of course, it's loop suppressed, so that's not so great. You can also look for photons that get radiated off of some fermion line. And so these happen at tree level, but then you have this broad continuum energy spectrum. And of course, that's harder to see as a signal. It depends on all sorts of astrophysics. I'll leave it to Tracy to talk about these sort of things in more detail. But suffice it to say, there are some great experiments that have been done looking for dark matter. This is a Veritas telescope, which point at some place like the galactic center and look for these photons. Here's Hawk in the mountains in Mexico. Here's the Fermi gamma ray space telescope, which is in space. And then sort of the great future hope is this Cherenkov telescope array, which is going to be sort of the LHC experiment of gamma ray astronomy. And so you can look with great power at the galactic center or dwarf galaxies or wherever. Okay, and this is kind of where we would be, well, where we are right now. There are limits on the annihilation cross-section as a function of dark matter mass coming from Fermi. And so they kind of require you to be below this black line here, okay, are the dashed lines. And here is this target cross-section I mentioned to you. And so if the dark matter is annihilating at this target cross-section, it can't be lighter than 30 GeV. So it's already providing some interesting bounds. And then CTA, when it comes in, will be able to probe regions way up here for dark matter that's say in the 100 to 10,000 GeV range. And we'll be able to probe them at this target cross-section. So it's extremely interesting if, say, dark matter is at the TeV mass scale. Okay, so given the time, I will kind of have to skip a little here, but I'm comforted by the fact that you will have a whole lecture series on indirect detection. Let me just say that neutrinos are an extremely interesting indirect detection target as well. And one can do the exact same thing. What I was hoping to do, I'm out of time, is to describe the basic physics behind it, describe some of the peculiarities of how results presented, and then give you some, the latest and greatest experimental probes. But some of that's in the notes, and I'll skip over through this. Neutrinos were an idea. Antimatter is very interesting, and has some great experiments, particularly AMS. Okay, let me leave those two, direct and indirect detection, but let me take this one question before I go. What do the colored regions of the predicted CTA bounds refer to on slide 53? So the colored regions here. That's a good question. I suspect, I'm not quite sure. I suspect it has to do with the time spent looking. So of course, the longer you stare, so this is from galactic center. Well, okay, I'm not sure actually. This is looking at the galactic center. It says here 500 hours. Probably what it is it depends on the halo profile. And so if you have a halo profile that is much more cuspy, where the dark matter is very concentrated as you get to the galactic center, you get larger rates. And so there are a variety of different halo profiles. I think you've heard about them in other lectures, and probably these are the bounds for different halo profiles. Okay. All right, so let me then come to the last topic, which I want to talk about here, which is particle collider probes of these things. And again, you'll have lectures on these, but let me just lay out some of the fundamentals. So how can you approach looking for dark matter at colliders? So the first thing is you might say, well, let's just look at, protons come together and make one dark matter particle. Well, no, that's impossible because dark matter has a Z2 symmetry probably, and so you have to make pairs of them. Okay, so I make two dark matter particles. Well, that's possible, and in fact, it very may be happening right now, or when the LHC turns on. But it's also useless because two dark matter particles is equivalent to nothing. You see nothing. And protons scattering into nothing happens all the time, right? So what you have to do is then think of a slightly more complicated process. One thing you could do is, if you're going to be working in the context with a bunch of other particles anyway, is make those other particles and then let them do whatever they do, decay down, and then you get dark matter at the end to look for that. Okay, so there are full models like supersymmetry, where you have all the superpartners' masses spelled out. Down here is the dark matter that you're interested in, but all these other ones come naturally for free in this context. And so at the, say, the LHC, you collide, make gluinos, then they decay in these cascades. At the very end of this cascade chain, you get the dark matter particle, one on this side and one on this side. And then you look for this kind of event. And what does this event mean? Well, it's characterized by missing ET because you've lost some mass and energy and momentum with this neutralino. And so you're looking for MET signatures. You could do this with these big full supersymmetric models. You can do them with simplified models where you basically say, look, this is just all this baggage for nothing. All I really want is dark matter and something to decay to it. And so you can do that, for example, in minimal dark matter models, where you just pull away all the garbage and just leave the bare centrals, have a few parameters, and plot search limits in those parameter spaces. Another approach is to do what's called WIMP effective theory, where you say, well, I don't want to assume a specific model. What I'm most curious about is, sort of a quark dark matter interaction, this blob that I actually had in my original figure a couple slides ago. And so I'm just going to parameterize this 4-particle interaction with a 4-particle operator, and just ask how well can I bound the existence of these various 4-particle operators. Now, again, just making dark matter isn't going to get you any visible signal, so you have to do something to it. So you have to like radiate off a gluon and then look for a 1-jet monojet signal, or radiate off a photon and look for a monophoton signal. And in fact, this is what was done in the very first papers on this back in 2004 by Berkdahl, Matchett, and Perlstein. Later on, this became a major industry where people basically considered every possible, Lorentz invariant operator. And so you see them classified. Here's one table where D stands for Dirac fermion, so that dark matter is simply Dirac fermion, and we just classify all the possible operators. Here, C is a complex scalar. There's a real scalar, and you just classify all these and figure out how well you can bound the sort of strength of these, the coefficient that comes in front. And so this is a beautiful way to do things, because once you're doing it this way, you can then compare across the direct and indirect detection and collider fields and see who's bounding what at the best, at the highest sensitivity. This has been fallen a little bit out of favor because it, of course, requires that you have an effective field theory. And if you have the LHC, which is running at incredibly high energies, it's not so clear that the effective theory is actually a valid approximation for some of the results you get. And so there is that caveat. But with that caveat in mind, this is a beautiful way to connect different fields and different search limits. Okay, so with that, I will finish, and I will just reserve this last section of WIMP variations for next time. And as I say, I hope it won't take an entire hour and a half next time, but it's some very interesting variations on the WIMP theme, which I want to discuss. Number one, to just emphasize that the WIMPs are not the end of the story. And number two, point out a whole bunch of interesting implications that we haven't had. For example, deviations outside the cold collisionless dark matter framework, which come from the WIMP sort of framework. So we'll talk about that next time. But let me stop here. There's some time, I can take some last questions, or else we can just be done.
Questions? It seems either everybody is tired, or which is more likely that you are very clear. I also don't see anything in the chat window. So, okay, let's thank Jonathan for the great.
Okay.
Thank you.
Thank you very much, and I'll see you tomorrow.